next chapter, I'd like to go back to the example we were doing last time, because I was writing with my fingers. So I want to make sure you understand this is an important example. Yes, this one. So let me repeat it. So remember, you have a homework due tonight. I posted next homework, but it's going to be due Sunday night. The reason I am doing that so that you finish and you concentrate on the preparation for the exam. Okay, so here we have a battery that has a potential difference of 10 volts and 5 capacitors. Each have a capacitor of 1 or 10 microfarads. What is the charge on capacitor 1 and capacitor 2? So we said the charge on capacitor 1 is easy. Okay, so this is capacitor 1 here. We know what's the voltage, we know the capacitance, we can determine the charge. So Q1 is going to be equal C1 delta V. Okay, and you can calculate that. You will find it's equal to, so what is it? Yeah, 7.89 10 minus 4. Sorry, yes, 1 10 minus 4 coulomb. Okay, so this is the first charge. Okay, the next one is we are asked for the charge on capacitor C2. Okay, and in order to do this, we cannot do it directly, unfortunately, because we don't have the charge or the voltage. So we cannot, we do not have the voltage. So in order to determine the charge, we need to determine the voltage. Okay, and in order to determine the voltage, the best way is to simplify the circuit, determine the equivalent capacitance, okay, and then work backwards in order to determine the charge and voltage for all the capacitors. So we named this C3, C4, and C5. So this is the figure that we have here. Okay, now, so let me forget about this here, because I'm going to just do, so C2 and C3, they are in series. So C2 and C3, so I'm going to call it C2, 3. This is the product of C2, C3 divided by the sum, C2 plus, let me put it here. So here, C2, 3 is the product divided by the sum, C2 times C3 divided by C2 plus C3. And so 10 times 10, that's 100. 100 divided by 20, that's 5. So this is 5 microfarads. Okay. Now, C23 is now connected in parallel with C4, and it's connected in series with C5. So the next step is to connect C23 and C4. They are in parallel. So let me call this C2, 3, 4. So this is the sum, because they are in parallel. So the sum of the two capacitors, we said capacitors in parallel, they add. Okay, so that's 10 plus 5, that's 15 microfarads, and this now in series with C5. Okay, so now we can determine C equivalent. C equivalent in this case, it's a series combination of C2, 3, 4 and C5. So we do the product divided by the sum. So this is C equivalent here. So the product divided by the sum. So this is 10 times 15 divided by 25. The sum is 25. So 10 times 15, that's 150, divided by 25, that's 6. So this is 6 microfarads. Okay? So now I'm going to work backwards. I will start with C equivalent. So first of all, let me determine, we have the voltage. So C equivalent, this voltage here is equal to V, which we said is V what? is 10 volts. Okay, so we know the voltage V, we know C equivalent, we can determine Q equivalent. So this is going to be C equivalent times delta V, which is 10, times V, which is 10. Here they call it V, so we'll use V. Yeah? So we have 6 microfarads times 10 volts, that is 60 microcoulombs. So this is the charge on the equivalent capacitors. Now the charge of the equivalent capacitor is the series combination of C234 and C5. We can determine what is the charge on them. Remember, series Q, that means capacitors in series, they have the same charge, but it's also the same as the charge of their equivalent capacitors. So from this series Q, we get that Q234 is equal to Q5 is equal to Q equivalent. So this is equal to 60 microcoulombs. Okay, so now I know the charge that is on C234. Okay, and since I know the charge, I can determine the voltage. So let me call this voltage here V234. Okay, so I can determine V234 delta V, we'll use V234, is equal to Q234 divided by C234. Okay, so what is Q234? It's 60 microcoulombs. What is C234? It's 15 microfarads. 60 divided by 15, that's 4 volts. So we know the voltage, V234, which is this voltage here. So this is the voltage between here. This is V234. Okay. Now, since I have the voltage, can I determine the charge on C23? We can, because we have the voltage, we have the capacitance, 5 microfarads. I can determine, so now I can determine Q23, it's equal to C23 times V234, which is equal to V23. So C23 we said is equal to 5 microfarads, and V234 is 4 times 4, so this is 20 microcoulombs. So now I have the charge Q23, which is the charge on capacitor C23. But capacitor C23 is a series combination of C2 and C3. So I can use series Q again. Series Q gives me Q23 is equal to Q2, which is also equal to Q3, and this is equal to 20 microcoulombs. So I had to work backwards. Determine C equivalent, determine the charge and the voltage of C equivalent, go backwards, determine the charge and the voltage of C234 and you can C5, and work backwards. So this is the trick at solving such problems. First of all, you have to determine C equivalent and then work backwards. Clear? So please practice this example on your own. Okay? And maybe I can do one more problem. Yes, so let me quickly do this one. Okay, so here this figure shows a parallel plate capacitor with a plate area that is given 5.56 centimeters squared and a separation D that is 5.56 millimeters. The left half of the gap is filled with a material dielectric constant K1, which is equal to 7, and the right half is filled with the material dielectric K2, which is 12. Okay, so what is the capacitance? So here we have 2 plates and they have 2 dielectrics. How can I determine the capacitance of this combination? Anybody makes a guess? Yes? Raise your voice. Well, so first of all, can I divide this into two capacitors? Yes. Are they in parallel or in series? No, they are in parallel. So here, let me make an equivalent drawing. So here, as if I have a capacitor C1, which is this one here, and it is in parallel with capacitor C2. Okay, so I have this is the equivalent of two capacitors that are in parallel, because you see they are connected here and they are connected here, so they are connected here and here. So this is equivalent. Remember, we did an example before in class where we had two dielectrics between the plates of capacitor, and we said we can think about this. So this is one dielectric and this is another one. Okay, we said we can think about this as two capacitors in series. Okay, here the geometry is different. Okay, so here we can think about these two capacitors as if they are capacitors in parallel. Okay, so let me determine C1. C1 is kappa epsilon 0. The area now is A over 2. The area of this here is A over 2, epsilon 0A, divided by the distance D. Okay, capacitor C2, this is kappa 1, is also kappa 2, epsilon 0. The area of this capacitor is also A over 2, so A over 2, and the distance is D. These two capacitors are connected in series, in parallel, so their combination, C12 is going to be C1 plus C2. So this is going to be epsilon 0 A over 2D times kappa 1 plus kappa 2. Okay, so now we have all the values of the area, we have the distance, we have the kappa 1 and kappa 2. We can calculate the equivalent capacitance, and you find it in this case it's just equal to 8.4 10 to the power 12 farads. Clear? Okay. All right. So let me now, any questions about chapter 25? Clear? So you have a homework due tonight. This is an important chapter. It will be in the exam, and so will be chapter 26. Okay. So let me go to presentation mode. Okay. Chapter 26 is probably the easiest chapter in this course. We're going to be speaking about electric currents, resistance. We will speak about a microscopic model for conduction of electrons in a resistor. Okay, we will speak about the dependence of resistance on temperature. Okay, and finally we will close the chapter with electric power. All right. So first of all, let us define the current. We did before say the current is the derivative of dq dt, but that was before actually this chapter. Okay, the electric current through a surface is the flow rate of net charges through that surface. It's a flow rate. In other words, it's the number of charges per unit time that are flowing through this surface. Okay, and interesting enough, even though in reality we know the charges that are moving through a conductor are free electrons. The protons, they are fixed to the nuclei of the atoms. They do not move. Okay. But we think for some reason, I don't know who came up with this standard, we always think about a current as a flow of positive charges. So in reality, we have electrons flowing in this direction. Okay, but we take current in the So these are electrons. We take the current to be opposite to the direction of flow of electrons. Okay, so this is a standard. So always current is in the direction of flow of positive charges, which is in reality it's really the opposite of the flow of negative charges, because we know in a conductor the charges that are moving are free electrons. Okay? The free electrons, when they move from an atom, they leave a vacancy. That atom is now a positive ion. Okay? That vacancy can move. The vacancy of the electron can move from one atom to the next. So, you can think about it this way. Let's assume this is an atom, and this is the next atom in it. Let's assume an electron leaves this atom. It leaves a hole, or a vacancy. Okay? So this now, because the electron has left it, now this is a positive ion. What is interesting is that this vacancy can move to the next atom. So this vacancy can move to the next atom. Okay? And so this, as if we have a flow of positive charges. When in reality it's not a flow of charge, it's really the empty hole in that atom is moving from one to the next atom. All right? So I just want to clarify this so you don't get confused. So in reality, the charges that are flowing are free electrons, conduction electrons. Okay, so this is just an aside. So the average current is defined as delta Q over delta T, which is the rate of flow of charges through the area divided by the time delta T. And the instantaneous current is dq dt. Remember, like we did in physics 121, we defined the instantaneous velocity and the average velocity. We said the average velocity is the delta x divided by delta t, the change in position divided by the time. And the instantaneous velocity, we said it's dx dt, the derivative of the position change with respect of time. Same thing here, the instantaneous current is dq dt. The units of the current is the amperes, and 1 ampere is 1 coulomb per second. So you know, this charge here is coulomb, the charge here is second. So the ampere, the charge here is ampere, and 1 ampere is 1 coulomb per second. Okay, this is what I was speaking about. So a current, so if we have electrons moving to the right, we take by convention the current is flowing in the opposite direction. So we know that really the positive protons, they do not move. They are fixed to the nuclei, so they are fixed, and the carriers, the charge carriers are really free electrons. This is the real world. Okay? Now, instead of that, we think, instead of saying current electrons are flowing to the right, we say positive charges are moving to the left, which is opposite to what is really happening. Okay, and hence the current is moving in the direction of positive charges, and this is the convention. This is an agreement. This is not real. This is not what is happening. We know in reality, as I mentioned in the previous slide, in reality it's the electrons that are flowing, but by convention we take the current to be opposite to the flow of electrons, and we say it is the flow of positive charges. Okay, so please make sure you know this dilemma. So why did they make this adoption of direction of current? Historically I don't know why. Okay, a current arrow is drawn in the direction in which positive charges would move, even if the actual charge carriers, which are electrons, are negative and move in the opposite direction. Okay, so it's just by convention. All right, let's now try. You have not probably in high school you did the Ohm's law and so on. Let's try to go into microscopically into the material, the conductor. Okay, so the conductor would have atoms and would have a free conduction electrons. Okay, if the conductor is not placed under a voltage, and there is no voltage, it's an electrostatic equilibrium, the electrons are moving, these free electrons are moving randomly in all directions. So really their average velocity, because if you take the average velocity of the electron is going to be zero. There is no clear motion of all of these free charge carrier in one direction. They are just moving randomly in all directions in a zigzag fashion. Okay? When we apply an electric field, and so we lose the electrostatic equilibrium, okay, the electric field will exert an electric force on these electrons. These are negatively charged electrons, so if you establish an electric field, they will move in the opposite direction of the electric field because they are negative charges. Remember, a negative charge, the force on the negative charge is opposite to the direction of the electric field. So if this is an electron, this is the electric field, the force that it will experience is opposite to the direction of the electric field. So now, when you establish an electric field due to an external voltage, these free electrons tend to be moving in this direction, okay? And let's assume they move with a velocity, they move with a drift velocity, they call it Vd. This is an average velocity of the electron in the direction of flow of these electrons. Okay, so this is a new concept. We're speaking about what is the drift velocity of the electrons. If you take any individual electron, we are not trying to determine the instantaneous velocity of the electron. We are trying to determine the average velocity of all of these electrons. Because when you establish a voltage and electric field, they tend to move in the opposite direction of the electric field with an average velocity that we call the drift velocity. Okay, so this is an electron and this is an electron. Really, they are moving randomly, but they are, because of an electric field, they have a drift velocity in the direction opposite to the electric field. This is what we're speaking about here. Okay, we want really to determine the relationship between the current that is established in this conductor and the drift velocity. This is what we want. So let's take a volume of the conductor, and it has a cross-sectional area A and a length delta x. So we're taking part of this conductor. This is a cylindrical conductor. Okay, and let's, for the time being, assume that we have positive charges flowing in the direction of the current. Really, you have electrons flowing in the opposite direction. But let's simplify things, and let's assume these positive charges are moving with a drift velocity Vd. Okay? Now, if you take any of these charges, in order for it to move a distance delta x, okay, and it takes it a certain time delta t, this Vd is equal delta x over delta t. So we can determine that delta x is really Vd delta t. So this is equal to delta x. Okay. The volume of this conductor, this element, is equal to the cross-sectional area times delta x. So this is the volume. Okay. Let's assume the number of mobile charge carriers per unit volume. These are charge carriers. Okay, per unit volume is n, small n. So n is the number. So small n is the number of charges, free charges per unit volume. Okay, and if we want to determine the total number of carriers, of free carriers in this volume, we can multiply small n, which is charges per unit volume, times the volume. This is volume. This is the volume. So this is, then you get the total number of free charges or free carriers in this volume. And we're calling it capital N. So don't confuse between capital N, which is the number of charges that are in this segment, and small n, which is the number of charges per unit volume. Okay, now what is the total charge in this segment? The total charge is going to be capital N times Q, the charge of each of these charges, and so it's E. Okay, so this is capital N, which is small n times the area times delta x, okay, times Q. This will give me delta Q, or the number of free charges in this volume element. Okay? So, if each of these charges is moving with a drift velocity Vd, okay, we know delta x is Vd delta t, so here we can replace this delta x by Vd delta t, because we have the average velocity, drift velocity, and we have delta x, delta t. We can write delta x as a function of Vd delta t. So we end up with this equation. Delta Q is equal n, which is the number of charges per unit volume, times the area, cross-sectional area of this conductor, times the drift velocity, times delta t, times the charge of each of these charges, which is usually E, 1.6 10 to minus 19. Now, since I have delta Q here and delta t, I'm going to divide delta Q by delta t, okay? And when I do that, I get the average current. Remember, the average current is delta Q over delta t. So let's divide. When I do that, I get delta Q over delta t, which is the average current. Now it's equal to nq, small n, times q, times the drift velocity, times the cross-sectional area A. So this is the equation that relates the average current to the drift velocity of the free charge carriers. Okay, so the drift velocity is Vd. You multiply it by the charge, which is usually E, times the number of free charges per unit volume, times the cross-sectional area of the conductor. It will give you the average current. You have not seen this before. You just use current P is equal Ri and so on. Now we are going into microscopically, okay, and trying to determine the relationship between the drift velocity of the free charges and the average current. So this is a new equation, and it's an important equation you should memorize. Okay, the speed of the charge carrier Vd is actually an average speed. It's called the average drift velocity or the drift speed. Okay. All right. Let's do a checkpoint. Okay, for this I will start the Kahoot. And start. And so this is the Kahoot here. And let me start it. So enter the Kahoot, please. Okay, so the pin number is 7074109. Everybody please join. Remember, I use this for attendance. Okay. So while we're waiting for players, please log into Kahoot. Okay, let me post the question. Okay, and I'll give you 1 minute to think about it and answer. Kahoot is slow today. The code is 7074109. Okay, so let me read it. Consider positive and negative charges of equal magnitude moving horizontally through the 4 regions shown in the figure. You have situation A, B, C, and D. So you have positive and negative charges, and the direction of motion is indicated by the red arrow. Rank the magnitude of the current in these 4 regions from highest to the lowest. Rank the magnitude of the current from the highest to the lowest. Yes? Which one? B and D. Yeah, so choose, ignore D, and choose, ignore B and choose B, ignore D. Okay, so your choice is going to be A, B, or C. Okay, so I'll give you okay, so let me start the Kahoot. We have only 10 seconds to answer. Okay, next. Five seconds. 3, 2, 1. Okay, all right, so we have 12 are correct and 18 incorrect. So we have, all right, let's see why. All right, so let's take this case. All right, we said by convention, we take current as the flow along the positive direction or the positive charges, when in reality there is no, it's negative charges. So what is the number of charges flowing in this case? To the right. Let's take to the right. We have 3 positive charges to the right. Okay. And we have 2 negative charges to the left. The 2 negative charges that are moving to the left, they are equivalent to 2 positive charges moving to the right. So here we have 5 charges and they are moving to the right. Okay, the next case. Here it's very simple. We have 4 positive charges, so the current is 4 and they are moving to the left. Okay. The case C, we have 2 positive charges to the right and 2 negative charges to the left, and we said negative charges flowing to the left are equivalent to positive charges moving to the right. So we have 4 positive charges moving to the right. Okay, now in the last case we have 2 negative charges flowing to the right, and we said current is in the opposite direction, so this is equivalent to 2 positive charges moving to the left. So the magnitude of A, so here remember I is delta Q over delta T, and we're assuming delta T is the same in this case. So clearly we have the current in A is going to be larger than the current in B, which is equal. These are magnitudes. We're speaking about only magnitudes. This is equal in magnitude to the current in C, which is larger than the magnitude of current in D. So the correct answer is B. So remember, okay, the current is flow of positive charges. So if negative charges are flowing in one direction, you can take the equivalent of that, but in the positive direction. Yes. نعم. لا احنا we know the current is the equivalent flow of positive charges. So here, for example, if they are showing 3 charges moving to the right, so that's current to the right, but the negative charges are moving to the left. The equivalent to those negative charges to the left is 2 positive charges moving to the right. So the equivalent situation here is as if we have 5 positive charges moving to the right. Same thing in this case here. So here we have 2 positive charges moving to the right. Okay, so there we said the current is in the flow, is the direction of the current is in the positive charges, is the direction of positive charges. Okay, so for example here there are no positive charges, at least this schematic diagram. There is negative charges moving to the right. So the current is going to be opposite to that. So it will be moved as if we have positive charges moving to the left. So the standard that we take for current, it's flow of positive charges, or the direction of flow of positive charges. I know it's a little bit confusing because when we know the reality, it's the electrons, the free electrons that are moving. Okay, but just so that you can deal with this. Okay, let's do this example together. A 12-gauge copper wire in a typical residential building has a cross-sectional area of 3.31 × 6 meters squared. Okay, this is the area. It carries a constant current of 10 amps. What is the drift speed of the electrons in the wire? Okay, we have an equation that relates the average current to the drift velocity. Remember, it's N, Q, A, Vd. Okay, N is the number of charges per unit volume. Okay, it says assume each copper atom contributes one free electron to the current. Okay, so in other words, if I want to determine the number of charges per unit volume for copper, for this metal, I need to determine the number of atoms per unit volume. So N is the number of atoms or charges per unit volume. We know 1 mole has Avogadro number of atoms. So I can write, this is Avogadro's number of atoms per mole. Okay, and this is volume, so I need to divide by volume of a mole. Okay, what is the volume of the mole related to the molar mass and the density? We know the density of the material is given by the molar mass divided by a volume of 1 mole. So we can write the volume V is going to be the molar mass divided by the density. So that's what I'm going to replace here. This is going to be equal Avogadro's number divided by the molar mass divided by the density, rho. So I will take the density to be in the numerator. So now I can replace this here. The average current is Avogadro's number times the density, rho, divided by the molar mass times the charge of the electron, or so E, okay, times the cross-sectional area that is given, times the drift velocity, Vd. So now I can determine, here they want us to determine the drift speed or the drift velocity. So Vd is going to be I, the current, the average current, times the molar mass, okay, divided by Avogadro's number times the density of the material times the charge of the electron times the cross-sectional area. Okay, they given us here the density and the molar mass of the copper. We can get it from the table of oops, let's see here. Okay, so this is the solution here. Okay, so this is the drift velocity, is the current times the molar mass divided by QA, Avogadro's number, times the density of the material. Q is 1.6 10 - 19. This is the area, cross-sectional area. Avogadro's number, 6.02 10 to the power 23 atoms per mole. This is the density. And so the density we convert from gram per centimeter cubed to kilogram per meter cubed. Okay, this is the current, 10 amps, and the molar mass of copper is so 63.5 grams per mole. So you can get that from the periodic table. So sometimes a statement of the problem in the physics book you have to look at the tables of elements. All right, clear? So here, notice in this problem, they specified the number of free charges is equal to the number of atoms. You might have a problem where they say the number of free charges is twice the number of atoms. So we have to multiply by 2. So you have to be careful. So this is, we use this because we were told that we have 1 free electron for every atom in the copper wire. Okay, so let me go back to presentation mode. Do not exit the Kahoot, we'll go back to it. Okay. Okay, so we said I is the instantaneous current is the derivative of the charge with respect of time. Okay, and so if we take the integral, we can determine that Q is the integral of the current. So if I want to determine the total charge that passes through a certain surface area in a time t, I can integrate the current. So let's assume I have either a plot of the current versus time, or I have an equation of the current. I can integrate from 0 to t and get the total number of charges that are passing through a certain surface area A. Okay? In steady state, usually when we refer to steady state, when there is no more variation, there is no more change with time. This is what we call steady state. And you will see in a future chapter, for example, when we charge a capacitor, originally there is a change of the charge, but then it reaches a plateau, and that's what we call steady state. Once it reaches the plateau, there are no more variation with time. This is what we refer to as a steady state. So in steady state, the current does not change with time, so we can write I is just, or Q, in this case, is just going to be IT, because the integral, I is not changing with time. So if you multiply the current by the time, or the time interval, you can get the total charge. Okay, these are some typical values of currents in we encounter. If you are using, for example, a scanning electron microscope, the current is in the picoamps. Okay, the neurons in our body, you know, the communication between cells, nerve cells, is through movement of an action potential. So you can say this is a current, but it's really a current of ions, a flow of potassium and calcium ions in and out of the neurons. But the current is about 10 to the minus 9 amps, nanoamps. A wristwatch is about 10 to minus 5. Your MP3 player is about 10 to minus 3 milliamps. Okay, a light bulb, like the light bulbs here, they can reach 1 amp. A fuse, usually many of the fuses we use at home and so on are 10 amps. So if you exceed a current of 10 amps, they will blow, and there will be no flow of, as if a switch is open. There is no flow of charges anymore, and that is used in order to protect your electrical appliances. So if the current is too high, it might burn your microwave heater, or your whatever, your refrigerator and so on. So in order to protect that, we use fuses that have a limit. When the current exceeds a certain value, it will melt the filament, and thank you, it will melt the filament. So these are typical values. Lightning from the thunder is about 10,000 amps. That's a lot of current. And remember, we did an example before, how much energy is stored in the cloud and so on. but we until now we have no way of harnessing the energy in the clouds. Okay. Now, if you take a metal or a conductor that has this shape, so it's the diameter is changing here, and if you take any sections through this metal, there is a section AA prime, a cut AA prime, BB prime, or CC prime, and you determine the current that is flowing is going to be the same. It's like a hose. If you have a certain flow of water in a hose, whether the hose is expanding in a certain region or narrower, the same flow of liters per minute is going to be the same. Same thing here for the current. The current is similar to the flow. It's charges per unit time. In the case of the hose, it's liters per minute or liters per second. Okay, so that does not change. The current is going to be the same. So we say, since the charge is conserved, there is no way for the charge to leave. There is empty space around this conductor. The current is the same in any cross section. Okay. So here is another example. So here we have surface A1 larger than surface A2, larger than surface A3. And if we have the steady state, the current through A1 is going to be the same as the current through A2 is the same as the current through A3. However, we will determine, or we will define current density. Current density, this is what we will define in the next slide, is current per unit area. Clearly, the current per unit area, so I1, let's call it I1 is equal to I2 is equal to I3. But if you take J1, which is current per unit area, the area here is larger. So this is smaller than J2. So here the current per unit area is larger because we have a smaller area, same current, smaller area, and this happens to be smaller than J3 because here the cross-section area is quite small and the current per unit area is going to be large. So even though the current is the same through these different cross-sections, the current per unit area is not the same, which would what we call the current density. Okay, so this is what we're defining next. The current density in the conductor is defined as the current per unit area of the conductor. So for example, here is an example. This is a cross-sectional area, a circular cross-sectional area of a conductor, and let's assume 4 coulombs are going through it every second. So the current is 4 amps. 4 coulombs per second is 4 amps. Okay, the current density, you divide the current by the area, and we are given the area is 0.2 meters squared. 4 divided by 0.2 meters squared, that is 20 amps per meter squared. This is the current density. Okay, let's take another conductor that has the same current. It's still 4 amps, except now the area is 0.4 instead of 0.2. And as you can see, if we calculate the current density in this case, same current, but the area is going to be larger, we obtain a smaller current per unit area. It's 10 amps per meter squared. So separate between the current, which is the flow of charges per unit time, and the current density, which is the current divided by the area that it's crossing. Okay, now we have proven this equation earlier. We said the average current is equal to the number of charges per unit volume, number of recharges, not number of charges, number of recharges per unit volume, times the charge of each of these charges, free charges, times the drift velocity or the drift speed, Vd, times the cross-sectional area of the conductor. Now, if we divide this by the area of the conductor, we get a nice equation which says the current density is NQ times Vd. It's equal to the number of charges, number of free charges per unit volume, times the charge of each of these free charges, times the drift speed of these charges. So this is another equation that we can use in order. So if I know NQ and Vd, I can determine what is the current density. I don't need the cross-sectional area. Okay? But if I'm asked what is the current, in that case I need to multiply that by the cross-sectional area in order to determine the average current. Okay, now this is Ohm's law. it's different from what you have seen before. Okay, for many materials, including most metals, the ratio of the current density to the electric field is a constant, and it is sigma. This is what we call the conductivity, sigma. Okay, sigma is independent of the electric field producing the current. So usually what we can write, instead of writing I is 1 over, 1 over R V, delta V. This is what you're used to do delta V is equal Ri. Now, we are, if we divide, let's see if I divide this by the area, okay, and divide this by the area, okay, yes, we will see that later on it will simplify, okay, because I did not introduce R yet, so we will do that later, okay. But now we are saying the current density, current per unit area flowing through a conductor is proportional to the electric field that is established in that conductor. Okay, and the proportionality constant is called conductivity. It's sigma, not rho, sigma. Okay, so the conductivity, the units is, you can verify, this is amps per volts per meter. Okay, because the electric field is volts per meter. Okay, the current density is amps per meter squared. Okay, so when you divide, you will have amps per volts per meter, the conductivity. And we know amps per volts is ohms, because V is equal Ri. So R is equal the, yes, amps per volt, sorry, it's 1 over ohms. Amps per volts is minus, because we have, you are familiar with this, V is equal Ri. So the units for resistance is ohms, which is volts per amps. Oops. Volts per amps. Okay, so this is what we call 1 over ohms. A current over voltage is 1 over ohms, because, and you have per meter. The 1 over ohms, or the inverse of ohm, is called Siemens. Very rarely used, but you can remember Siemens company, German big manufacturing for medical devices and so on. So Siemens per meter is another unit that is used for the conductivity. Usually, you are familiar with resistivity. Resistivity is actually 1 over the conductivity. It's the inverse, 1 over the conductivity. Resistivity, okay, and it's in units of ohm meters. It's the inverse of the conductivity. So resistivity, which is rho, is equal 1 over conductivity, 1 over sigma, okay, and hence we can write this. We can write it as the electric field is equal to the resistivity times the current. Resistivity times the current. So whichever you remember, either the current density is equal. Yes. Sorry. Sorry. Here, these are confusing. Thank you for pointing that. So the resistivity is 1 over conductivity. Yeah. Okay. It's very easy to confuse between them. You just inverse one. It's like the 9 and the 6. Okay. So let's determine what is the equation for a resistance. Okay. So let's assume we have a conductor with a length L, and we establish a voltage difference delta V across this conductor. Okay. And let's assume we have a current I flowing through the conductor. Okay, so we know the electric field is equal the resistivity times the current density. This is what we have seen in the previous slide. Okay, and I can write it also in vector form. We know the electric field is really an electric field vector, so I can write it rho times J, and I can write also J as a vector. So this is a vector J, for example. Okay. The resistivity, as we mentioned, is of a metal is in units of ohm meter. It depends on the metal. From one metal to another, they have different resistivity, and so the resistivity is equal to the electric field divided by the current density. Okay. Remember, when we studied uniform electric field, and let's assume here we establish a uniform electric field in this conductor. The conductor is not in electrostatic equilibrium anymore because there is a voltage. Okay, so the electric field is, or the magnitude of the electric field is delta V over L. Okay, so we're going to set this equation that we know before is equal to this equation that we have introduced in the previous slide. Okay, and now we know the current density is current per unit area. Now we can get an equation. So if I divide delta V by the current I, this is going to be equal to the resistivity times L divided by the cross-sectional area, rho L over A. This is what we call resistance R. The resistance R in ohms, R is the resistivity of a material times the length of the material divided by the cross-sectional area of that material, rho L over A. Did you study this in high school? Yes. Okay, so we have just proven that relationship using these equations of electric field, the relationship between electric field and the potential difference, and the fact that the electric field is equal to rho, the resistivity, times the current density, current per unit area. Okay, so you need to remember this equation. And what is important, that the resistance of a resistor does only depends on the resistivity of the material and depends on the geometry. Its length per cross-sectional area. Okay, and its units in ohms or volts per meter. Okay, so remember, the resistance is R is the ratio of the potential difference across a conductor to the current in the conductor. So you can say R is just delta V over I. Okay, R depends on the material resistivity rho, okay, and the geometry, which is the length and the cross-sectional area. Resistivity is a property of the material. If you move from copper to silver to gold, they have different resistivity. Okay, and you can so usually we can measure the resistance. If you use a multimeter or an ohm meter, you can measure the resistance of a certain metal. Then you measure the length and the radius. You can determine the resistivity of that material. Because using this equation, you can easily measure L. You can measure the cross-sectional area of the conductor, and you can use an ohm meter or a multimeter to measure the resistance R, okay, which is the voltage divided by the current. How does a multimeter measures the resistance? It passes a current and it measures the voltage. Okay, knowing the current and the voltage, it will give you the value of the resistance. You get the value of the resistance, you can determine the resistivity of the material. Okay, so Ohm's law, the current through, this is the other version of the Ohm's law. The current through a device is always directly proportional to the potential difference applied to the device, where we can say delta V is equal Ri. This is what you are familiar with. So this is the new form, or the old form, I guess, of the Ohm's law. Okay, this law is not always valid. Okay, the assertion is correct only in certain situations. For example, for certain devices like a diode or a tungsten lamp, this is not correct because the material is not ohmic material. It does not obey Ohm's law. So Ohm's law applies usually for conductors or certain kinds of conductors, but does not always apply. And so a conducting device obeys Ohm's law when the resistance of the device is independent of the voltage polarity or the voltage value. So if you take a resistance, okay, and you connect it to a power supply, a voltage, and you start changing the voltage and you measure the current, for example. Whenever you divide the voltage by the current, you will find the same value. meaning the resistance of this material is not dependent on the voltage. That's what we mean. This is an ohmic device. However, some materials, like tungsten, for example, when you start changing the voltage and you measure the current, and you divide the voltage by the current to determine the resistance, you find it's not constant. It varies. It varies with the voltage. In that case, we say this material, tungsten, is not an ohmic material because it does not obey Ohm's law. The resistance is not independent of the voltage that is applied. Okay? So remember this, for those who are in electrical engineering, you probably have used diodes. The material of a diode, the PN junction, is not an ohmic device. You know, when you plot the IV characteristic, you do not get a straight line. So let's look at, so here is a resistor, and if you start changing the voltage, let's assume this is a circuit. So you have a battery, delta V, and you connect to it a resistor R, okay, and you measure the current. You put an ammeter to measure the current, okay? And when you divide delta V by I, you get the resistance R, okay? If you plot the current versus delta V, you get a straight line. So the slope of this straight line anywhere is the same, okay? And it's equal to 1 over R. Slope, because R is equal delta V over the current I. So here, the slope is equal 1 over R. So in this case, this is an ohmic device because any voltage I pick, I get the same value of resistance. I measure the same value of resistance. However, if I connect, for example, so this device obeys Ohm's law, we call it an ohmic device. This device, which is a lamp, this is a tungsten lamp. So this material here, this filament here is made of tungsten. It's, when you connect it to a power supply and you start changing the voltage and measure the current, okay, this is what you get. If you plot the current versus delta V, you don't get a straight line. You get something like this. Okay, so clearly, if you try to determine the slope anywhere, so for example, the slope, it's not constant, which is 1 over R. The slope is 1 over R. You can see for this material, at different voltages, you get different resistances because the slopes are different. Here, the slope is 0. The slope is 0, meaning the resistance is very large, almost infinite. And here, the slope is very high, means the resistance is very small because the slope is 1 over R. Okay? So we say because the resistance is varying with the potential difference, we say this material is not ohmic. All right? The diode also has almost the same behavior. If you plot the IV characteristic for a diode, you get this around 0.7 volts, 0.6 or 0.7 volts. So if the voltage across the diode is less than this value, there is no current flowing. It's like a valve. As soon as the voltage increases above 0.6 or 0.7 volts, the current starts to flow. So it's like a valve, and in this case we say the diode is not an ohmic device. It's not a straight line. The resistance is changing with the voltage that is applied. Okay, next Kahoot. All right, so look at this, and then we will move to the next Kahoot. So here we have 3 situations, 1, 2, and 3. Each one of them we have the same voltage, delta V. Okay. But what varies is the area. One has area A, the second one area A over 2, the third one is area A over 2, and what changes also is the length. The first one has a length L, second one has 1.5 L, and the third one has L over 2. And we want to determine the order of the currents. Okay, rank the current greatest first. Okay, so rank the current greatest first. Remember, R is rho L over A. R is the resistivity times the length divided by the cross-section area. So I will give you half a minute. Okay, let me end the show and move to the discard and move to the Kahoot. Okay, so, all right, so this is the result. Next. Okay, so answer the question. I'll give you a minute. These things, you cannot do them mentally. You have to write. You cannot do it just by looking at it. Huh? You have to have a piece of paper and something and scribble. Ready? Oh, most of you did not have paper before, so. Okay, for the sake of time, I need to move. Okay, and should we start? Okay, let's start. And you have 10 seconds to answer. Huh? So choose between A, B, C, or D. Five seconds. Okay, so we have 17 correct and 15 incorrect. Okay, so let's do it together. Okay, again, I do not do it mentally. I can't. Okay, I have to write down. So I have a current I1. I1, we said Ohm's law says it's delta V over R. What is R? Delta V. R is rho L over A. So the length is L, the cross-sectional area is A, so it's rho L over A. Okay, so this is I1. I2. I2 is the same voltage, delta V, and R2, this is the resistance R2. So what is R2 now? It's delta V, okay, R2 is the same material, so it's rho. The length is now 1.5 L, okay, and what is the area? The area is A over 2. So this becomes delta V over rho LA divided by 3, which is I1 divided by 3. Clear? I3, now it's also delta V divided by R3, and this is delta V. What is R3? R3 is rho, the same resistivity, same material, L over 2 divided by the area over 2. The area is divided by 2, so 2 and 2 will cancel, and this is going to be equal to I1. So clearly here I1 is equal to I3, and it's larger than I2. Okay, so the correct answer is C. نعم. Yeah. First of all, the resistivity is the same. It's not changing. Resistivity. The resistance changes. The material is the same, so it has the same resistivity. What changes in this case is the resistance, because we're changing the geometry. When you change the resistance, since the potential is the same, delta V is the same for all three situations, the current is going to change. The current is equal the potential difference divided by the resistance. So the resistivity is not changing here. Yeah, so okay, now you determine the resistance change. That does not mean that's the current, because the current is delta V over R. It's the inverse. I know. You have to be careful. Pay attention to the question, what it is asking. Okay? So, let's go to next one. All right. So here is a problem where you have to be very careful. So here we have iron that has a resistivity of 9.68 10⁻⁸ ohm meters. What is the resistance of the block? Notice we are given the dimension of the block and we are given delta V. So the resistance here, okay, is rho L over A, rho L over A. But what is L here? Clearly this is L here. Because the voltage is applied between this surface and this surface, this is L. What is the cross-sectional area? The cross-sectional area is this one. So this is now rho times L, which is 0.15 meters, divided by the area. This is a square, so it's 0.012 squared. Okay, now look at the next question. Now it's the same dimension, except the voltage is applied between two different surfaces. Notice delta V now is applied between this surface and this surface. So even though the equation is the same, but the length is not the same. What's the length here? Exactly. So this is now the length. So this is times 0.012. And what is the area in this case? The area is now 0.15 times 0.012. So even though it's the same block, but because in one situation the voltage is across placed at across these areas here, the second case it's different areas, you get different resistance. So this is a very good conceptual question. I can give you this and tell you, are the resistance equal, different? And then so you might say, oh, this is the same block. They're equal. They're not equal because the potential is applied across different surfaces in the two situations. Okay, so you have to, you know the equation, but you have to know where is L. L is along the length between the potential, the surfaces at which the potential is applied. That tells you L. The cross-sectional area is perpendicular to the L, to the length of the conductor. Okay, so these are the values here. Okay, so this is one, in the first case 100 micro ohms, and in the second case is 0.65 micro ohms. It's even, it's 0.5%. It's not even 1%. It's 0.5% of this one. Just by changing the way we apply the potential on the same block, we get totally different resistance. Okay? All right, I will stop here. Okay, any question about what I have covered so far? Okay, the homework I posted is due Sunday night, and I did it on purpose because I want you to finish the homework. It's easy because it's about ohm resistances and current and so on, so that you can spend more time on the midterm. Please solve as many all exam questions as possible. The exam will have so we have 5 chapters, 22 to 26. Each chapter there will be 1 question, and each question will have 2 parts. So you will have 5 problems. Each problem has 2 parts, and you will have 1 hour and a half. And it is on March 10th at 7:30. The more examples or problems you solve, the easier the exam will be, and the better your grade will be. As simple as that. It does not have to do with intelligence. It has to do with hard work. The harder you work, the more you solve, the easier the exam will be and the better your grade will be. Believe me. Okay? We'll see you inshallah tomorrow.